bread and butter question. You've got to be able to get full marks on this question. Okay? And I would expect this question would be worth 4. Okay? 4 marks. 4 easy marks. Okay? I don't want to see any of you lose marks on this kind of question. Not just because it's simple and you guys can do it, but also because for the next 1.5 years, the questions you'll be doing will all build on this kind of skill. Right? So if you don't have this foundation, right, we're in trouble for later. Alright? Typical question. Find the stationary points, determine their nature, then let's draw the graph. Now, even though it doesn't say showing all features, blah, blah, blah. See how it says hence, right? So even though it's only worth 2 marks, they're expecting you to include all of the things from earlier parts of the question. Alright? So let's give this a go, shall we? Find all stationary points. What do I need to do to find stationary points? I've got to differentiate, okay? Now, I've also picked out this question because it's a classic error to make in it, right? What you've got is a quotient. So the instinct you've got, especially in an exam when you're under pressure, is go to the quotient rule, right? But you shouldn't. Why not? Because you can divide it up, okay? And then you just get 2 fractions which are really easy to deal with, rather than doing VU dash minus UV dash on V squared. It'll be a disaster, okay? So, how do I break apart? X squared on x is just x. And the other part's 1 over x. Simple. That's a little more manageable, okay? In fact, I might write this as x to the minus 1, because that'll help us when we differentiate. Okay, so, derivative. Just take each piece one at a time. Derivative of x is 1. Derivative of x to the minus 1. What do we do with it? Bring the power out the front, so minus, and then reduce the power by 1. Okay, so far so good. Now what? What do I do with this derivative? Good. Now, by the way, please don't just say, we've said this before, don't just go next line, 1 minus 1 on x squared is equal to 0. Okay? Because it's not, but we want it to be for a particular case. So put your logic in, okay? 4 stationary points. Okay? The derivative is 0. Okay? And what that means is this expression which we just worked out, that's equal to 0. Okay? Can anyone tell me what the values are we're going to expect?
Plus or minus 1.
Good. Okay, so there are the x values. Now, find all stationary points and determine their nature. Okay, so I've got a little more to go before I've actually found it. I know where its x is, which is horizontal, but I'm going to need to know where its y is. Okay, so how do I do that? Good. Okay, so when I say x equals 1, y is going to be equal to 2. 1 plus 1.
Do you have to show your full subbing in and stuff?
Okay. We will have to show some for working, but you'll see later on. Okay. So there's one of our stationary points. Okay. And the other one, x equals minus 1. Minus 2. Now, at this point, you ought to be getting suspicious because there's a lot of symmetry here, right? Which we should have picked up earlier. Because what kind of function is this? Look at it carefully. Okay. Think back to further graphs from Locus. The top part, x squared plus 1. Picture x squared plus 1. What kind of function is it? It's even. The bottom's x, which is odd. When you have even or odd, if you divide them or multiply them, what you're going to get, the result is also odd. You see that? 1, 2, right? Minus 1, minus 2. Okay. So you don't need to, it's not part of the question to say, show this is an odd function, right? But the whole reason we dwelled on odd and even functions is because they help you do things like this and it makes it faster. Okay. Alright, so 1, 2, and minus 1, minus 2. Okay, so now what? I've found them. What do I have to do? Okay, so to determine their nature, you will remember we've got 2 options, right? What are the 2 ways we can go about this?
Second derivative.
Okay, second derivative or first derivative. Okay, now have a look at this function, and this is its derivative. which way do you think we should go? Should we use the first derivative and draw up the table? Or should we do the second derivative?
Oh, no. I'm terrible because you get 0.
Secondary doesn't seem like it'd be that
You won't
hard.
because when you
Secondary.
secondary.
What's the thing that makes us choose? What, you know?
If it's x is 0, then obviously, like, if it's
It will be simpler because it's just.
Let's just remember the way that you go about this, okay? If you're using the first derivative, okay, what you have to do is for each and every stationary point, okay, you have to test values on either side, okay? And then you want to show what the derivative is doing. It's going up and then going down, or vice versa, okay? And then you say it's a maximum or it's a minimum, okay? That's with first derivative, right? With second derivative, what do? You don't draw this table. What do? You just pop it in, right? You just take one value, as it were, okay? So which is less work? This is less work, provided that differentiating is not hard, okay? Now, is it hard to differentiate this again? It's not. It's not, right? Because this 1 disappears, okay? This minus x to the minus 2, you just do the thing again. It's a polynomial. That's about the easiest thing to differentiate, apart from exponentials, okay? So, I think we should elect to go the second derivative, all right? Remember, you can use either, but we're trying to save time here, right? Okay, so I've got, I'm forgetting about the 1 because it just disappears. I've got minus x to the minus 2. Okay, so bring the power down. Watch out for the double negative, okay? And then reduce the power by 1. Okay, now what? Good. So I've got my 1 and my minus 1, okay? So when x equals 1, what's the second derivative?
2/1.
Good. Okay, now hold on. What does this mean? Second derivative is positive, which means it's facing up, right? Okay, if you can't remember what concave up looks like and what it means, you just draw it, right? And that means it's a local, sorry, I should say relative. It's a relative minimum.
You know the local and relative thing?
Yep.
How'd you get that?
How do you know what's...
It really doesn't matter. I'm saying relative because
to
it's just
mix
policy.
Are you allowed to say local?
Local sometimes and relative other times?
Are you allowed to say local and absolute?
Oh, I see what you mean.
Or something like that.
Yeah, I suppose so. Though that seems a bit, I mean, it's like, do you do the one question in millimeters and meters at the same time? Oh, I suppose you could, but why would you? Anyway, okay, there's one. Now, do you have to say it's concave up? Can you go straight from here to here? The short answer is, yes you can. Does that mean you should do it? I don't think so. Okay, here's why. Remember, this is our first time assessing your ability to understand all of this. Okay, so what I'm looking for as a marker is not just do they write down the right stuff, but can they demonstrate they know what this all means? Okay, like this is greater than 0, so what? What does that indicate? Okay, why is it a relative minimum? Is it just like because a maths teacher said so? No, it's because it indicates this geometric feature, which is a minimum, right? You can see it looks like a minimum, right? So that's why I write it. I mean, I've been doing this for years and I still write it. Okay. Got to do it for the other one, okay? When x equals minus 1, the second derivative is... Okay, odd function. By the way, did you notice odd function, right? First derivative is even, x squared. Second derivative is back to odd. Okay? Every time you differentiate, you flip between odd and even. Anyway, so this is concave down. All right. Now, since this is a question all on its own, okay, you should actually conclude this question and actually have a sentence, right? So you would say, therefore, okay? I've got these two stationary points and I'm going to say what their nature is, right? So I'd say 1, 2 is a, which one was this one? This one is a relative minimum. And the other one is the other thing.
If you press in time, does that add any marks to your if it's in time?
No. It's one of those things which the information is there. However, with something like this, I think it's particularly valuable because you can see that all of this actual information, which is my answer, it's sort of scattered throughout all of my work. So as you don't want to give extra work to the marker to try and find your stuff and fail to find it and say this is not worth what it should be. Okay? Right. Let's graph it, shall we? You've got... I need another colour. Who's graphed it already? Anyone?
Yeah.
Okay, good. This will be quick. The first thing you do is take the information you've already got, right, and plot it on there. Okay, so 1, 2 up here, and it's going to be a minimum. Okay, so I'm expecting it to come up like that. All right. And of course, I'm actually not going to worry about the other side because once I've got this side and I know what it looks like, it's an odd function, remember? So I'm just going to draw it across the other way. All right. Apart from our calculus, what other features do we know about this thing? Good. Now, that's the kind of graph it is. What kinds of important features does a hyperbola have? Okay, good. So, where's the first asymptote? The simplest one.
X equals 0.
Good. Don't forget to label your asymptotes, please. Okay. So that makes sense of why this stationary point is a minimum. It's going to draw back up over here. Okay. So far, so good. What happens towards here, the right-hand side?
Y equals X.
Okay. So it's approaching, and you can see that, by the way, from here. Right? Because you have that 1 over x part which is disappearing. Okay? So you can draw your y equals x asymptote in there. Again, critically important to actually label it and make sure you're approaching it. Okay? Now since we worked it out in part A, you should actually full on label that and say this is 1, 2, and you could even say it's a minimum turning point. Okay? Now that I've got that, I'm just going to mirror it across the other side. So yeah, that'll do. Finished. Okay, of course this graph, because of the features that it has no intercepts, but if it did, you'd have to graph them on. Okay? Any questions about that?